Welcome my old friend Nalini. She did admit that I could say how long I've known her, which is 29 years. So it's been I've known her for a long time. We were quite young then. And she's from the University of Sydney and is going to talk on life and mathematics.
I hope this is on. Thanks, Peter. I wish you hadn't used the adjective old, but we have known each other for a very long time. I wanted to start off by thanking the LMS Women in Mathematics Committee, and in particular Beatrice Palloni, for persuading me to come all this way to give a talk about something that I would never normally talk about, at least to a larger audience. And that is what I've called life and mathematics. Because it's something that I don't normally talk about, it was a very difficult talk for me to prepare, and I hope that, well, you'll forgive me for some of the abrupt changes between three different subjects or topics, which are to do with my life and then my work and then some reflections on the above too. I thought somewhat hard about how to talk about my life, because I think an important part of this exercise is to see how each of us has come to be what we are. It's something that I think is useful and very important to do, no matter what gender you are. And so I thought hard about how to do that, and I decided that, with Beatrice's permission, that one of the best ways I could do it was to present to you a video that was made of an interview with me by a woman called Trixie Barreto, who works at my university in the faculty office, but does creative filming as a hobby in her own time. And she saw some of my remarks on Twitter and decided that she should do a film of me. And so that's what I'd like to start off showing you first. It's a 9-minute long video, and then I'll come back to the slides on these three different things. So let's see if this works. Okay. I think as a child I felt I didn't really belong anywhere. I think I started to retreat into mathematics as a haven. I want people to feel about maths the way they feel about music. My name is Nalini Joshi, and I'm a mathematician. My parents were born in Burma. I was born there. My brother was born there. It was a very wild sort of place. You know, creeks, countrysides, all kinds of amazing things. But several things happened. The terrible government that they have now, that came into being in 1962 with a coup. One of the distinguishing features of this government was that they wanted to make the Burmese ethnic group be the dominant group in the governance of the country. So they started by making sure that people of different ethnic backgrounds didn't have influential positions. At least that's my understanding of things. So they, for example, took all the Indian professionals of Indian background in Burma and conscripted them into the army. So all the males. So my father was conscripted into the army because he was a doctor, and they couldn't let him be in the capital cities. So he was posted to far-flung places, and so we got to live in some of those regions of Burma. That was in our army days. The guy in the middle was a soldier who looked after us, in a sense. That was the time of my life where I felt like a free animal, ranging anywhere I wanted to almost. Thinking back on it, I loved that period, which my mother says was the most terrible part of her life. I absolutely adored it. I loved it. And then it became clearer and clearer that life was going to get more and more difficult because I was from an ethnically Indian background, not Burmese. With those kinds of reasons in mind, my dad decided we should emigrate. So we came to Australia. I think as a child I felt I didn't really belong anywhere. I was the ethnic minority in a country where people were interested in praising the people of a different dominant background. When I came to Australia, again, I was different. I still had, for a long time, I remember a lot of very odd ways of pronouncing things that my friends laughed at. I think I started to retreat into mathematics, in a sense, as a haven where I could work out things explicitly and completely to my heart's content. There were things I couldn't explain in real life, but if I went into mathematics, I could explain things to myself and understand everything. So I think that's why mathematics became a kind of a feature. I wanted to be an astronaut, to tell you the truth, but when I went to my careers counsellor and talked to her about this, they said, well, you have to be a little more realistic, dear. I would try and reproduce planetary motion with dinner plates and, ordinary objects to try and understand why it is that we only ever saw one face of the moon from the Earth, things like that. But there was nobody I could talk to about these things. Whenever I asked questions of my science teachers, it's like we were on different planets, literally. I mean, because I wanted to get some deeper understanding of things that wasn't really possible in that setting. So really I wanted to go to university to study science. I wanted to become a space traveller. But the thing that was, because as I said, my father was a doctor, he expected me to become a doctor. For him, being a doctor was a matter of survival. This is what saved him from having to languish in the backwaters of a country like Burma. It's what enabled him to emigrate and actually do something to support his family. So that's what he expected. And unfortunately, I disagreed with him. So the first day of enrollment, I went and I said, I don't really want to do medicine. Can I change to science? Since they were used to people asking the opposite question, they said, oh yes, of course. So I changed my enrollment, came back, told my dad, and he didn't speak to me for the next month. Yeah. Anyway, he got used to it. So I decided maths was the way to go. And that's how I became a mathematician. I don't know that gender had anything to do with it, but it did turn out that I'm the first female professor of mathematics of any kind here at Sydney Uni. The systems that I work on occur as a kind of a universal framework for almost all areas in which nonlinearity in that system is balanced by something else. Imagine that you've got two stars coming together and they're going to intersect with each other. Maybe they won't actually bang into each other, but they'll go past each other. Will they get destroyed? Will the big one destroy the little one? Will it come out the other side? The ones that survive, the ones that always have this property that they are transparent to each other, are the ones that are the most productive, the most fruitful, the most powerful systems we know of for describing what will happen a long time into the future. These are the types of systems I work on. I work on their mathematical properties. I try and work out when this property of being integrable, that is solvable, in a very unique sense. When those properties can be identifiable in any given system that you might give me. I've been on radio shows where people ring in and say, why do you need mats? What's the point of it all? The cashier can just do it automatically at the checkout on a machine. And I'd say, yeah, that's true, but what you want is the brain to go along with the instrument so that you know when the cash machine is spitting nonsense. When you go home on the train, you see lots of people doing Sudokus. That's just mathematics. The patterns, the way you logically work out which number goes in which square, that's mathematics. I want people to feel about maths the way they feel about music. I don't know how to explain it. When you play music, no matter what type of music you're interested in, what type of instruments you're interested in playing, there is an emotional feeling. There's an emotional satisfaction. There are patterns in the music that repeat. There are variations in music that you can play with. I want people to be able to do that with mathematics. Mathematics is not a monster. It's actually as human as you and I are. It is as human as music is. It is as emotional as music is. It's something that you only need a little bit of work to get in through the door. Once you're through the door, you start seeing things that you never expected to see. It's the patterns that underlie the numbers, underlie the arithmetic, that is what I'd like people to be able to see. Along the way, you get to a place which is incredibly deep and very satisfying when you see it. I think as a child, I have to stop that now. Where are we? Okay, so I try not to watch that video. It makes me too emotional. That's a little bit of a glimpse into what got me into mathematics and how I see it. So let me give you a slightly further point of view. Oh, before I do that, I just wanted to let you know that this video is available on Vimeo. If you'd like to download it or watch it or whatever, you can. And Trixie Barreto is the person I mentioned who actually created the video. Okay, so in more explicit terms, what has life been like as a mathematician? Well, a very long time ago, as Peter intimated, I started doing a Bachelor of Science at the University of Sydney, and at the end of my honours year, which is a fourth separate year in the Australian system, I decided that I really wanted to go further with mathematics and applied to and got into Princeton to do a PhD with somebody called Martin Kruskal, who is was a very unusual and very original thinker in mathematics. So I did my PhD at Princeton, and I was lucky enough that my boyfriend was also able to come to Princeton to do a PhD. He was in training to be an oceanographer from Australia, from Sydney University as well. And halfway through my PhD, we got married, approximately, it was in 1984. Yes. And then after that, we came back to Australia, and my first job was at the Australian National University in Canberra. I was a postdoc first, and then I became what they call the research fellow and lecturer, and had our first child there in Canberra in 1988.
And let me tell you, it's a very interesting experience to go and give lectures with baby vomit in your hair. It does make you a very open person to whatever you meet in the course of a day. And then after that, about 3 years at ANU, I went to UNSW, the University of New South Wales in Sydney, where I got my first tenured job. And I started there in 1990 and got promoted there to senior lecturer. I had my second child in 1993, and then I gave up tenure in 96. You see, the way I was able to survive as a mother and a mathematician was to have a very supportive partner, my husband. And other speakers have also mentioned how important it is to have somebody who's willing to share that journey with you. But the cost of that was that my husband couldn't get a job. He was going from one position to another on soft money grants that were held by other people, and it was time for him to seek a permanency somewhere. And the job that he got as a permanent job was in the Department of Defence in Adelaide, so we had to move from Sydney to Adelaide, and the only way I could do that was to get a job that didn't have tenure. So, and I asked at UNSW, would you be willing to have me back? Perhaps you could hold my job for me for a few years. I will promise to come back. And they said no. I can tell you more about those kinds of things if you're interested, and I hope we'll have an interactive discussion at the end. So I gave up tenure. That was scary, but the thing that saved me was I was able to get a senior research fellowship funded by the Australian Research Council, which went for 5 years. And so I spent 5 years approximately in Adelaide, and in that time I was still able to apply for promotion, so I went from senior lecturer to associate professor. And at the end of that time, I applied for and got a chair at the University of Sydney. I still remember going to the dean at Adelaide University saying, I got offered a chair. It's a wonderful opportunity for me, but I'd really not like to move because my husband has a job here. Would you be able to offer me something? He said, oh, times are tough. The budget is very tight. I could offer you a beginnings position as a lecturer. And I said, oh, no, I don't think so. So I went to Sydney, where I've been for the last 11 years, and it turns out that the Department of Defence is a very, very forward-looking organisation, and my husband could come to Sydney and live there, even though his job is still in Adelaide. So he goes back periodically, but not for very long periods, and that's the way we've managed to have solved the two-body problem for the last 10 to 15 years. So at Sydney, I've been a professor, as I say, and the University of Sydney is where I started as an undergraduate, so it's really a very interesting full circle to come back to. When I came back to Sydney, there were still people there who taught me when I was an undergraduate, and I was a professor of applied mathematics, the unique professor at the time, and so that was another interesting nuance on how to deal with people and become a leader, I suppose. Yet another conversation we could have. So, but I think that this picture really encapsulates all the different stages that one has to go through. There's not only the babies that you have to deal with, the circumstances of childcare, which is, I think there's a nanny up there somewhere, and the inbox, and now the email inbox that never ever stops. It accelerates in its fullness from day to day. There's also the colleagues, the bosses, the demands of the system one might be embedded in that you have to constantly be juggling with. But I guess I'm here to say that you can do it. And it's worth doing it if you're really, really engaged in and driven by mathematics. So, where am I now? Just very recently, about 4 months ago now, I was able to start, I was offered and started the next 5-year fellowship that I was able to get as part of the Australian Research Council system. It's called the Georgina Sweet Australian Laureate Fellowship. That fancy name reflects a person, Georgina Sweet, who was the first scientist employed at a university in Australia. She was a parasitologist. You can read about her life story on the web. It's not a pretty story, but it's worth looking at as a contrast between what used to happen about 110 years ago in Australia and what happens now. So along the way, between arriving in Sydney and here at taking up this fellowship, I was head of school for 3 years. I became president of the Australian Mathematical Society. That was for about 2 years plus 1 year at the beginning and then 1 year at the end as incoming and outgoing president. Then I became chair of the National Committee for Mathematical Sciences, and now I'm still chair, and along the way I got elected to the Australian Academy of Science, and now I'm a member of council of the Australian Academy of Science. And there are many, many other things hidden in the ... there that I won't take up time here talking about. But this pathway to some extent reflects one of my important messages, which is, I think, also reflecting one of the elements of the after dinner speaker last night, whose name I didn't write down, the president of the hall we've been staying at, New Hall or Murray Edwards College. She mentioned that giving back as an important part of building your life, and I think I can echo that very strongly. This was my way of giving back, to become head of school, not because you want that position or the authority, but to contribute in a way that helps to shape the culture of the organization you're in. I think that's an important way of giving back and of shaping the field or the profession. To become president of the Australian Mathematical Society was also, in that sense, my way of giving back. I mean, I could just spend the rest of my life crabbing on about the way things are done, or I could go out there and actually help to change it. And I think it's important to contribute in that way. So I guess that's part of my message here, not just to enumerate the different things I've done, but to encourage you to think about those kinds of ways you can be involved. It doesn't matter what stage you're at in your career or your education, you can always be involved. So now let me skip ahead to talk a little bit about my work and mathematics. I mentioned in the video that I work on integrable systems. That is a term that's very widely used in many different ways. The way I think about integrable systems is that they are nonlinear equations. They may be differential equations, partial differential, or as in the case of the Korteweg-de Vries equation, or ordinary differential equations, as in the case of this first Painlevé equation, or they may be discrete in one variable, n here being the discrete variable, or there may be many discrete variables, in which case you have partial difference equations. It doesn't matter what form they take. What's important about these equations is that they are solvable through, in quotes, solvable through an associated system of linear equations. So if you've heard about soliton theory or inverse scattering transform method, then you might know what I mean. The Korteweg-de Vries equation, for example, arises as the compatibility condition for an associated system of linear equations which involve a spectral parameter. And by looking at solving the problem in that associated spectral plane, you can then invert the picture to get back information about the solution of the original nonlinear equation. And that method, called the inverse scattering method, or inverse scattering transform method, was one of the major advances in the mathematical sciences starting in the 1960s, and it's had an enormous impact in many other areas. The equations about which I've been obsessing for a very long time arise as reductions of those equations, and this is the first one of them. There's a list of 6. There are many more, actually, but I'll come back to that the work that I've actually done on these in a few minutes, and in particular give you a little flavor of what I'm doing now. So why are these interesting? Why is it, I mean, I've told you that there's been an enormous impact, but I think that one of my favorite ways of explaining why I'm doing what I'm doing is in terms of this very simple picture. You all know that mathematics starts with counting. You start with integers. Allowing multiplication and division leads you to rationals. Solving algebraic equations, polynomials, leads you to algebraic numbers. And then there are the others, the numbers that you get like pi, which can't be expressed in terms of any finite expression involving the earlier known numbers, integers, rationals, and algebraic numbers. What I'm looking at on the right-hand side of the slide are functions that play similar roles to those numbers. So integers, polynomials, there's a kind of a direct way in which you could understand the field of polynomials, like you might understand the field of integers. Then there's rational functions, algebraic functions that come from solving polynomial equations. And then beyond those are transcendental functions, things that you all know and love, like the exponential function, that's a transcendental function. The gamma function, the hypergeometric function, and elliptic functions, they're all transcendental functions in the sense that they can't be expressed in any finite way in terms of these earlier known functions. The equations that I'm dealing with and their solutions are even more higher transcendental than these earlier known transcendental functions. But rather than being esoteric and irrelevant, they turn out to be providing you with universal information about models in physics. For example, in random matrix theory, string theory, and others, there turns out to be models that are universally given, and they are solved in terms of the solutions of my favorite equations. So there's justification for my obsession. In trying to extract information about these functions, I'm actually, creating things that are like the log tables that used to be created by people a long time ago. So I'm really, I think of myself sometimes as treading in those footsteps just because I like to do mathematics, but at the same time it's connected with those applications, and I find that very satisfying. So here is the first Punleve equation, again, abbreviated as P1. Or in system form, I can rewrite it as this coupled system of equations. And if you've done any course in dynamical systems theory, you know that there are ways of trying to understand systems of equations in phase space, or the space of these two coordinates, or in terms of the original equation, it would be in terms of W and W prime. There's a Hamiltonian description. There's a total energy, in a sense, or a Hamiltonian associated with this equation. But it's unusual in the sense that the Hamiltonian is itself t-dependent. So it's not conserved in time, but nevertheless, there is this deep structure underlying it. And as I said, the solutions are very transcendental, and they are meromorphic functions with what I call movable singularities. So to give you a flavor of that, let me come back a step to elliptic functions. These pictures are taken from the Digital Library of Mathematical Functions, which is available free on the web. It's dlmf.nis.gov. So what these are showing you is that as you walk in the complex plane, which here is given by real and imaginary parts x and y, you have a sequence of periodically spaced poles. There's a periodic array of such poles, and the equation for the elliptic functions can be integrated once. It's very similar to the equation I just wrote down a moment ago in terms of the Hamiltonian here. It's extraordinarily similar, except that here, instead of having a constant, I have a variable. So if I now think about these functions, how can I extract information about them without necessarily having all the tools of analysis of differential equations theory? Well, there is an alternative point of view, and that is the geometric point of view, which would be very familiar to those of you who are in any algebraic geometric setting or number theoretic settings. You'll know already about these curves. The first integral that I wrote down can be thought of as this polynomial in two variables. And instead of studying the differential equation, we can study the properties of functions that parameterize these curves. So if I call this f, then the level curves, f equals minus g3, are the curves on which my solutions live, and so I can get information about them by studying these curves. Oh dear, I was hoping this picture would show. Let me see if it comes up in a moment. But you can plot the level curves of these, this function. It's very easy to look at particular values of G2 and G3, and what you'll see are a picture like this. Remember that what we were looking at was something like this, and in the xy plane, what you find, and in particular for these values, you'll see that you get, first of all, a component of the curve over here, and then as you change G3, you get curves that look like these. And the place, the special one that crosses itself over here is attained when you have a very particular value of G3 when two of the roots of this cubic collide, they coalesce. So this is a very well-known way of looking at these complex algebraic curves, and Frances Kerwin was here yesterday, and she's written a very nice book on complex algebraic curves where you can go and study properties of such curves and the beautiful mathematics that underlies them. So what I did was to try and understand this point of view for the Punleve equations. Remember that the solutions of Punleve 1 are meromorphic. They have poles, and the poles can move around in the T space. So what happens as you go into the places where you start having a pole in the local neighborhood where you're standing? Well, that's a very easy way to look at it, and that's to look at projective space. So instead of the affine coordinates x, y, you can identify that in terms of the projective homogeneous coordinates, u, v, w, and in that case, the polynomial I'd written down earlier becomes this. And you can see here that when this denominator, what was the denominator here, w, when that vanishes, this one goes, and this one goes, and you're left with only the u cubed term. So you have a point which is given by u being 0 and w being 0, and v being anything you like, scaled to be 1 in this context, and you get a point which is a point at which all of these curves go through it. And that's called the base point. This is a base point of the pencil of elliptic curves. The curves that I wrote down over here are also known as the Weierstrass curve, elliptic curves, and they all go through the base point, which lies at infinity because that's where w is 0. So over there in my picture, if you were to follow one of these curves and you go off to infinity, then you just switch to the new coordinate system, which is given by these ones, and you'd be able to understand what was happening there. From my purpose, I want to understand the solution of a differential equation, and so as a dynamical system, I need to know how to go through such a point. At a base point, you have many curves coming in. It's like a traffic accident where all the cars on the highway are collided with each other, and you need to know how to walk away from it, how to disentangle the cars so that they can continue along some unique path. And that process of resolving the flow was something that became clear was very important technique for me to understand these equations. So for those of you who don't know this field, blowing up a base point or resolving a base point is a technique that's very standard in algebraic geometry. Here's a very simple example. There's a singularity of this curve at the origin when x and y are 0. Try plotting it, you'll see that there's a cusp there. And the blowing up process is to simply take one of those variables as a quadratic in the new variables. There are many ways to do blow-ups, but this is the standard, simplest way to approach it. And if you put this into the equation, you'll see that the polynomial factorizes. If you put away this term for a moment, you see that the original curve, which had a cusp at the origin, now becomes a parabola at the origin. And what you've done is to smooth the curve. And in fact, you need to do this several more times in order to resolve that singularity, to get a good resolution, and to understand what's happened to the functions that parameterize this curve. So that's what I did with Dijkstermaat. This is my most recent work. It came out about 2 years ago. For Panleve 1, it turns out that there's a sequence of 9 blow-ups you have to do. I won't go through all the detail of the notation here, but it's incredibly similar to the elliptic case, except that one of those base points you have to blow up is time dependent. And I've rewritten time as z here. There's a scaling you have to do before you can write down these answers. And only the last step differs from the elliptic case. But by doing it this way, we were able to understand the flow of the solutions along curves in the resolved space, which is a topological space that's compact, connected. There is a sequence of exceptional lines that you have to walk around as you go through this space. And it turns out that the last step, the last line that you get, is exactly where the poles reside in the solutions. And another way to think about it is to, instead of thinking about it as lines intersecting each other, think about each line as a node. An intersection between 2 lines means 2 nodes are connected. And if you do that, you get a Dynkin diagram, which is the Dynkin diagram of an exceptional Lie algebra, which turns out to be the most complicated Lie algebra in that list originally classified by Killing. So this is actually the affine extended E8. And so what I did was I started out with the most simple Panleve equation in the list of all Panleve equations. You couldn't get simpler than that, but I have the most evil initial value space in which I can understand the solution. So this is going to be the job of a lifetime, further lifetimes possibly, in which I can try and understand the dynamics of the solutions. So that's in a nutshell what I did, and I wanted to give you a little bit more of a mathematical flavor of what you're able to do by going into this geometric point of view. And one of the things was that in this initial value space, and I should have explained that the space which we've labeled here as S9 is dependent on the independent variable, what was called t before and now called z. And so this is not a steady picture. It will change with z as you walk around in the z complex space. But this space is called Okamoto space in honor of Okamoto, who was the first to do such blow-ups. He did that in 1979 for all the Panleve equations. But we're doing it here in a certain asymptotic limit as you go towards infinity in the z space. And in this space, you can try and understand the dynamics. First of all, the exceptional lines form, the union of the exceptional lines forms a set that we call the infinity set, and we were able to show that that infinity set is a repeller for the flow. So if you're in the Panleve space and you get close to one of these exceptional lines, then you immediately go away from it again. You can understand the limit set in terms of the complex dynamics. The limit set, omega, here we were able to show is non-empty, connected, and compact. we're able to show that every solution of the first Panové equation has infinitely many poles, surprisingly something that nobody had proved before in complex space. And I can go through the elements of the proof, but if you're interested, if you like, ask me for details later. But the main idea is that if that set intersects, the limit set intersects L9, then we can show that it intersects it again and again and again. So you already get an infinite number of poles. But so let's assume that it doesn't. If it doesn't, then it must be a compact subset of Okamoto space. But in that subset of Okamoto space, which is got the infinity set quotiented out, the function is analytic because we don't have any poles. And so what we have is a holomorphic function on a compact set, so it can only have one limit point. But we know that the autonomous limiting system has two limit points, so there's a contradiction. So it must intersect the line of poles and therefore have an infinite number of poles. So what I'm doing now is to try and extend that point of view to the discrete equations, for which we have really no toolbox available to us like we do for the differential cases. And so I started out by looking at Sakai's classification. He has a beautiful paper in 2009. He classified all possible second-order equations whose initial value space, or the Okamoto space, is regularized by a 9-point blow-up. And he found all the Panové equations and known discrete versions of them and new discrete versions. So my idea is to use geometry to try and understand their solutions. This is a kind of an audacious idea, and I don't quite know how to describe it. I think I'm often seen as an audacious, driven, obsessive, and difficult person because I have my own ideas that I'd like to be able to use to solve problems. But this is actually a difficult thing to do, it turns out. I would have thought that it was good to have new ideas. But, and here is my second, I suppose, important point. These are just little quotes that I've actually had thrown at me. I'm not trying to be what's the word? To provide you with a self-pity. I'm trying to say that these are comments that anybody can get in any context, no matter what your gender is, but they have an impact of a kind that you need to be able to deal with. Okay? So when I was a PhD student, I had this amazing guy who was a full professor in a very prestigious US university, already had a full career. I was giving my little poster. He came and put his stand. He wasn't scheduled to do a poster. He put a poster stand next to mine, put up his published paper, a printout of his paper, and proclaimed to anybody who came along to my poster, "Mine is much better than hers. Come and look at my poster." Okay, how do you deal with that? Well, I can tell you if you're interested later. When I was a postdoc and then having my first baby, comments like, "Babies need mothers." That's true, but would they say it to a male colleague? And does it have an impact on how they perceive your work? When I was at my beginnings of the first tenured position, comments like, "Oh, we note that all of her papers are with XXX," who was my PhD advisor. Okay, that's a factual comment, but what implications does this have for the way they're judging your work? There are many implications, and one needs to tease out and be able to rebut all of them. And this is what I'd like to put in front of you as something that you need to be aware of. Okay, other comments. Your area of research is very narrow. True, but you could say that about almost all of mathematics. No matter what you're expert in, you're going to be expert in dealing with a certain type of problem. And that's because mathematics is an incredibly rich and diverse area, and nobody can know all of it. Okay? if it turns out that the research is of importance in a different area, it doesn't matter how narrow it was. It's something that's important to do other things. Okay, and these are some other comments I've had. I've gone for a lot of grant applications, so this is from an assessor's comment. Asymptotic does not appear in the database of NSF grants. Yes. Does algebraic? You know, it's not a criticism, but okay. We have to thank Nalini for reminding us of what Boutroux did in 1913. Now, Boutroux was Painlevé's student, and he was the one who started looking at the asymptotics of solutions of the Painlevé equations. He has two very big papers. It's true that he did start that process, but there are many, many, many questions that still remain open. And to say that what I'm doing is only reminding the audience of what he did is a way of putting my work down, by at the same time being very civilized, right? Okay, you have to find ways of rebutting that too. This was one of my latest assessors reports. She may be well known in Australia, but not known overseas. So that was easy. All I had to do is to point out that I'm actually a visiting professor at Leeds University. They must have thought they were, you know, appointing somebody else if they didn't know me. Okay, so these are things that everybody has to deal with. It's not just female mathematicians. If you work in the corporate world, if you watched any of the movies that come out about the corporate world, you'll know that competition is alive and well, and competition is one of the things that everybody has to deal with. The question is, how will you develop your way of navigating a path through that and maintaining your own generosity of spirit? That's the important question. And I was reading an interview with Elizabeth Blackburn recently. She's an Australian originally and works at UCLA, I think, in California at least. And she's a Nobel Prize winner, won it for her work on telomerase, the little tips of DNA strands, chromosomes actually. And she said, this struck me, she enjoys being free to explore territory where she would not have ventured before. This is after her Nobel Prize. I would have been a little afraid to do things because my male colleagues wouldn't have taken me seriously as a molecular biologist, she said. Now this is a Nobel Prize winner who got to this stage of her life and is still harking back to that aspect of the criticism that was so important in shaping her career. So think about that and where you are in terms of those kinds of restrictions on your own creativity. This is a very, very big word which may not apply in all contexts, but it's a word that I learnt recently. And as soon as I read about it, I thought, oh, at last there is a terminology for this. It's called microaggression. And it's invented by psychologists, not by mathematicians, this word, from the 1970s. It says, it's brief and commonplace, daily verbal, behavioral, and environmental indignities, whether intentional or unintentional, that communicate hostile, derogatory, or negative connotations. So we are living in a modern age where everybody knows about equal employment opportunities, everybody knows about discrimination, but there are nuances in the way conversations happen that you need to be aware of, and microaggression is still alive and well. So being able to name it is something that's important. You might want to think about that. And let me say that this is not restricted to female, certainly not to female mathematicians, but it applies to everyone, once again. But these are issues that I think not many people talk about, and this is an occasion where I think it would be important to talk about such things. So how did I survive? I survived by finding my own resources, finding my own friends to work with. And that is an incredibly empowering thing to do, I think. Even if you don't get the grants, you can find a collaborative friendship with people. And I think Gwyneth talked about this yesterday. So important to find people whom you can talk to and bounce ideas off. And that's the way I survived. So I now have had more than 20 grants, totaling some large number of dollars. I've had 2 5-year fellowships, which has been incredibly important. I'm on the second one now. The first one certainly saved my career because I gave up tenure to get there. There's a very interesting backstory to that one as well. I was counting my collaborators to tell you how many I have now, and really I was surprised to find so many. I've written papers with over 40 people. I've had more than 20 postdocs, 10 PhD students, and I find it's wonderful to be able to attract people to work with you. And for me, students are one of the most important parts of my life, to be able to convey my dreams and not beat it into them, but to inspire them with the same dreams is wonderful. Okay, so to encapsulate, I think I see mathematics as, I think of it as playing. It's really a creative game. It's creative play at a very deep level. I find it most satisfying to be able to do that playing or creating with friends. I love inventing new ways of doing things, hence my directness and obsession with doing these things, to invent my own way of doing things. And to me, it's incredibly important also that what I'm doing is contributing to understanding the world. And going back to some of the earlier aspects of my career, there are issues. There's a very long list of issues that I've just only very briefly touched upon. And we talked about the first one yesterday in the discussion group that was in this room. There is something called the imposter syndrome, which is a name for the condition, I suppose, in which people feel that whatever good that's happened to them must be the result of a fluke accident, or somehow because they were faking it, or that they didn't actually deserve it. That's called the imposter syndrome, and it's very widespread. And if you feel it, and I'm sure some of you have, and I have, you should be able to sit down and say, actually, that's just not true. Let's check with evidence which part of this is true, if any. And you should be able to see that this is kind of like a lack of confidence rather than anything else. Many other issues, and what I'm trying to do is to use those as marker points in events that I'm trying to hold, I will be holding. As part of my Georgina Sweet Fellowship, I have the responsibility to try and support women in research in Australia and mentor early career researchers. So we're going to have events at which we talk about such things, and by highlighting the life and careers of female speakers at these events. So the first of those will start in September this year. So once again, recapping what I've already said, I think these are the things that sustain me, and in particular the fact that mathematics has no boundaries or borders, for me, is what drives me. I couldn't do anything else now. Thank you very much.
Does anyone have any questions?
So you mentioned briefly about going back to Sydney, where you had been an undergraduate and working with people who've been your lecturers. Could you say a little bit more about how you, I don't know, sort of got into your
So it depended on the individual. I found that much of what I had to say was foreign to the way they saw careers. So the reason they had stayed in their jobs for 40 years and not gotten very far in their career was because they were very rigidly holding on to particular ways of seeing the world, and I tried to encourage them out of those ways. So I succeeded in some cases by encouraging some of them to go for activities that would lead to promotion, and that worked in 2 cases. The others I had to gently encourage into retirement.
Considering your interest, why didn't you decide to do theoretical physics instead of mathematics?
Because I have no physical intuition whatsoever. I did want to do physics, as I explained in that video. I wanted to become an astronomer, basically, astrophysicist. But I got to first year uni, and in the first term, like in the first 4 weeks or something, people got onto Gauss's theory of electrical distributions on a spherical surface. And they were doing surface integrals, and I'd never seen them before. And I wanted to understand how to do surface integrals without being told, oh, you just do this. This is that step, and if the sphere happened to change slightly over there, then you just do the same thing. I really found that deeply unsatisfying. And in experiments, I was constantly failing. I did first year chemistry as well, and there was one famous time when you had to you were given a certain number of amount of some substance. I've forgotten what it was. You had to dissolve it in some solvent, and then you had to go through a process to extract back what you've dissolved and identify it. At the end, I got more than I put in. So there was no way I could do these things.
Okay. Thank you, Nalini. Actually, just before we thank Nalini for the talk again, say that Nalini's party trick, as was recently said on Twitter, is that she can write down from memory all 6 Pavlov equations. Now, you saw the first one, it's short. The longest, the 6th one is long. Anyway,
I'm not sure I can do it anymore.
You were credited as being one of the few people in the world who could do that. Anyway, so let's thank Nalini again for